Greetings, physicists. This video will be demoing how to solve friction and drag problems. So we'll start with this one. Got this lady who wants to move her sofa. So she puts those little, they're like felt discs if you've ever bought them. They slip underneath the pokey bits at the bottom of the sofa, and that makes it easier to slide across the floor because they have a very low coefficient of friction. And she's going to push it, and it tells us how fast she pushes it. And we want to know how hard that she is pushing on this sofa. So let's take some givens here. We have the sofa's mass is going to be 32 kilograms. We have a coefficient of friction, and I think we have to assume that this is a sliding coefficient of friction, not a static coefficient of friction, so a kinetic. So we'll say that mu k is equal to 0.080. No units on u. And she pushes it at a steady 0.4 meters per second. So her velocity, which is a constant velocity, is equal to 0.40 meters per second. Now, I would argue that the word steady is more important than the actual number there, because it tells us that this is a constant velocity. So if we have a constant velocity, our acceleration is 0. And that is very important. So let's then see if there's anything else. And our unknown is the force that she applies. Well, this looks like there's going to be more than one force involved, especially because this is a friction problem. So let's do a free body diagram for all this stuff. All right, and if it helps to draw the free body diagram, you can also draw a picture. So here's the sofa. All right, sofa's a big blocky thing. It's got little dudes on the bottom there. It probably has the sofa sliders, which I'm not going to try to draw. And she is going to push it across the floor. So the system here must be the sofa. That's what's being pushed. So I'm going to draw that sofa as a dot, as a particle. Let's give it some arrows. We know mg will pull down on it. The normal force will pull up on it. We're going to assume she pushes horizontally. I think that's the only way to solve this problem. So her horizontal force is just, we'll call it F, and then friction will resist this. Now, if the acceleration is 0, then it has to be that the friction equals out and balances her force. So I'm going to go ahead and put a lowercase f back there. And I tried to draw it the same length. I think I drew it a little short, but that's okay. Well, from our free body diagram, we can get two sigma f's, one in the vertical direction and one in the horizontal. So let's do that. In both cases, though, the acceleration is 0. So the force forward, if we make forward the positive direction, subtract the force backwards, because the friction is in the negative direction, should equal ma. Remember, a is 0, so really we're saying the force that she applies is equal to the frictional force. In the vertical direction, we have the normal force. If I make up positive, minus mg downwards, because downward, I guess, will be negative in this case, will be equal to ma, but again, a is 0, so that whole term can go to 0, and the normal force can equal vmg. Now, the one more thing I need, because this is a friction problem, is the friction equation. So let's draw that in here. So we'll have that the force of friction, lowercase f, should be equal to mu times the normal. Now let's do some substitution here. I don't know the force of friction. That was not a given. But and I'm not actually looking for it. I'm looking for her force, her F. So her force F should be equal to this lowercase f here, which is the mu normal. So I can say the force she applies, which is my unknown, is equal to mu n. All right, that's my first solve step, is combining those two equations. But I know that n is equal to mg, so I could also say that the force she starts with is equal to mu mg. And I do have all of those things. So now I can do my substitution. So the force she applies should be equal to mu, which was 0.080, no units, times the mass of the sofa. It was a 32 kilogram sofa, and g in this case, of course, is always 9.8 meter per second squared. I'm in kilograms and meters per second squared. Those are the right units for me to get force. So now I just need to take my calculator and multiply this. So 0.08 times 32 times 9.8, and I get right at 25. 25 newtons of force is a reasonable amount of force to expect her to be able to output. It's actually 25.088, but I went ahead and rounded. 2 sig figs is good here. That's about what we have. So she pushes at 25 newtons of force to move that sofa. So get yourself some sofa sliders, because if this, you can imagine, if this coefficient of friction was 10 times rougher, 0.8, and 0.8 is also a reasonable thing, especially if you have carpet. I should be using 250 newtons of force, and that's not trivial. Okay, let's go on to the next one. Wherever it is. Here we go. A lawn roller, if anyone's a gardener out there. It's kind of like an old-fashioned mower, except it's just a big, heavy, its mass is important as opposed to the blades. And we're going to use it to flatten out our lawn, because who wants a bumpy lawn? And a couple questions here. Should we push or pull the roller in order to make it easier on us? And then the other question is, what's more effective if we're actually trying to flatten the lawn out? Do we push it or pull it? So this is a conceptual question. Love me some conceptual questions. And we assume that this is directed along the handle, whether we're pushing or pulling. So let's make some free body diagrams. I think that's going to be key here. So if, and I'm going to say that the object of the system is this roller here. That's the thing that's going to do the work. So if I'm doing it like here, it's got an mg down. I am going to draw the normal force last when I do these free body diagrams, I think. So let's say that in this case I'm pushing. Now if I'm pushing, then my force goes down the handle in this direction. So I would push like this. And so that's my force, my applied force. And that's at some angle theta, right? That's not parallel with the ground. So if I were to look at my force has a horizontal component and it has a vertical component. And that vertical component is straight down. There will be friction. So essentially, if I'm going to push that roller, and most people are not going to accelerate when they do this, you're just going to want to walk at a constant pace across the lawn. That's the easiest for you. So you're going to apply the force, whatever force it takes, such that your horizontal component forward just cancels out the frictional force backward, because there will be friction between this thing and the grass. So that's going to determine how big you make your force, is so that you make this arrow longer and longer until this arrow balances this arrow. Now the longer you make it, the bigger the downward component will be. And so now look at what's down on this force. You have this downward component here, and you have mg. So together, the normal force has to beat both of those. Well, not beat it, it has to equal both of those. So I'm going to draw my normal force up to be larger than gravity. That's there. So that's the situation where I'm pushing the roller. Let's think what happens when I pull the roller. So I'm going to draw another free body diagram over here. If I pull the roller, then my force goes up this way. So let's draw some things. Gravity should be the same. Gravity doesn't care about how I'm pulling, it just cares about the mass of the roller, and that should not be changing. But my force now is going to go back this way. Well, I've drawn my arrow about the same, and of course the angle. Let's assume the angle of the dude doesn't change; that it's still at some angle theta. But I think I need to alter my arrow here, because here's what's going to happen as I pull backwards. As I pull backwards, again, I have some component that's going sideways, and that's what's going to overcome my friction force. But friction is a mu times a normal. Well, the mu is whatever the coefficient of friction between grass and steel is. I'm assuming this is a big steel cylinder. So this is not changing. But the normal is, because when I pull at an angle like this, there's a vertical component to my pull. So I'm actually reducing the normal force, because in order for this to be balanced, the normal force then has to be less than gravity, because I'm adding this component to it. So my normal is going to be less, and if my normal is less, my friction is less, and if my friction is less, I don't have to use as much force on my pull, because I don't need as big a sideways arrow to overcome it. So this is a very interesting problem. Now let's go back to our two questions. Our two questions were, one, which is easier to push or pull? And I think in terms of easiness, I'm going to go with the one that means I have to have a smaller force. It definitely takes less force to pull the steel cylinder than it does to push it, because I reduce the normal and I reduce friction. So that's nice. Well, then it says, which is the most effective at flattening the lawn? Well, while this one here is easier on me, notice that it produces the smallest normal force, the force between the lawn and the steel cylinder. And if the goal of the tool is to push down the lawn, I actually want a bigger normal force. And that bigger normal force will be a bigger push on the surface of the lawn, and it'll flatten it out quicker. So in this case, making it easier on me, it'll save my shoulders perhaps, but I may have to be out there longer because I'm not going to be flattening the lawn as much with that free body diagram. So some things to consider. You probably didn't know the physics of lawn maintenance were so interesting. Assuming you thought that was interesting. All right, on we go. Okay. We got a filing cabinet we're going to take in a dump truck and dump it at the dump. So let's draw this. So you're going to have some dump truck. Let's see if I can make my stylus work here. There we go. Dump truck. Dump trucks are these guys, right? They have the big thing, and they can tilt the bed, and then the filing cabinet is here, and we're going to tilt it and make it slide off the back into the dump. All right. The filing cabinet is steel. The truck's bed is also made of steel. When they start telling you materials, that may mean we're going to have to look something up. And we say, what is the static friction when we tilt this to 20 degrees? And what angle will we have to tilt this at for it to slide off? I'm going to solve this one first, and maybe you'll see why. But let's start with some givens. Well, we definitely know how heavy the cabinet is. That's a given. If we're asking what angle, then the 20 degrees is not a given yet. Wow, only one given. This could be rough, ladies and gentlemen. Well, there is another given of sorts. There's the steel, and there's the steel, and they're saying at what thing will it begin to slide? At what angle will it begin to slide? Well, if it begins to slide, that means that's the point at which we overcome the static friction. Static friction is what keeps something from sliding. So that will be the maximum static friction it could possibly get. So we know we're looking up, when I go to look up steel on steel, I have to Google what is the static coefficient of friction between steel and steel. You can do this a lot. There's a big list that I know of, engineering toolbox, that has a whole bunch of coefficients of friction. So Google it or ask Siri, what is the coefficient of friction between steel and steel? And what I come up with when I do this is 0.8, as long as that's not lubricated steel, because there's a whole other thing for lubricated. So the mu, no, there. The mu static, in this case, is going to be 0.80. Done. All right. This should be enough. Now, let's, of course, do a free body diagram. We're going to need that. So here I come. We're going to have, that's the cabinet. It's got gravity straight down. It's going to have a normal force, but notice that there's an angle here. So that normal force is going off this way. And then it's going to have a friction force, but remember the velocity is this way, so the friction force has to be opposite the velocity. Once it starts to slide, it would be going that way. Even when it's not sliding, right? This is still a static problem, so it's not sliding yet. So we take the friction force to be the opposite direction of where it would be sliding once it starts moving. So I'm going to still make my friction force back this way. And friction and normal always have to be 90 degrees to each other. That's a rule. So what I'm going to do here is actually rotate this so that it's easier for me to picture. I'm going to take my entire free body diagram and rotate it until the normal is straight up. You don't have to do this, but it's what I do because it makes me, it's intuitive. And then I'm going to rotate, and then the friction force will be this way. I know the direction of motion is to the right. That's not an arrow I put in my free body diagram, by the way, because that's not a force. But it rotates my mg to be in this direction. Well, how much did I have to rotate that? Well, essentially it was an angle theta, so I had to rotate it theta degrees. And if my mg was down and now it was here, it's rotated from down, where it used to be was here. That angle that it rotated must be theta degrees. Now I can split my mg. All right, so this here, by the way, if you're ever asked on a test, draw the free body diagram, this is the free body diagram that does not include the splitting. The splitting is an analysis tool that you will use to solve the free body diagram, but it's not technically the free body diagram itself. So don't draw splitting forces in your original free body diagrams. All right, so but when I split it so that I can analyze it, I should have my friction back, my normal up. If I'm making this into a triangle, I can see that this is the adjacent side and this is the opposite side. So my mg is my hypotenuse. So adjacent, that goes with cosine, opposite goes with sine. So the forward one, which is the opposite, which should be equal to the friction there, will be mg sine theta. And the downward, which is opposite the normal, will be mg cosine theta. All right. So here we go. Let's make our equations from this. Our sigma f equation in the horizontal direction. If I make mg sine theta the forward and friction the negative, so I'll say mg sine theta minus friction equal to ma. But this thing hasn't started to slide yet. It says what angle will it start to slide, but at that point we're really saying what is the maximum there before it starts to slide. So I'm going to say the acceleration is 0, so that I could say mg sine theta equals the friction. That's the horizontal. The vertical, where it's definitely not accelerating, is normal up minus mg cosine theta equals ma. But again, the acceleration will be 0 in the vertical direction. So do this here. I can say that the normal has to equal the mg cosine theta. And because it's a friction problem, I'm going to need this equation. I'm going to have the friction equal to mu times the normal. But we know what the friction is, and we know what the normal is. So let's put those in. Okay, the friction was equal to mg sine theta equal to mu times the normal, which was mg cosine theta. I can see a lot of stuff is going to cancel, which makes me very happy. Mass cancels. It does not matter how heavy that filing cabinet is. It could be the biggest file cabinet in the world, or it could just be this little tiny plate of steel, and it would start sliding at the exact same angle, regardless of its mass. How cool. It doesn't matter if you do this, whoops, come on. It doesn't matter if you do this on Pluto, or on Earth, or on the surface of Jupiter, even assuming that were possible. The gravitational constant doesn't matter. That's cool. At least I think that's cool. So what do we get? I'm also going to be solving for theta, right? So let's get all the thetas on one side. So let's divide by this dude. So we have like this. And that's going to even simplify the problem a little bit, because there's a trig identity there. So we've got sine over cosine, that's just tangent of theta equals mu. This problem became a lot easier now, and I haven't even plugged anything in yet. We know mu, so tan theta is equal to 0.80. So all I have to do is take the inverse of that. So I need to take tan minus 1. Tan minus 1 of 0.80. So let's see what calculator says there. Inverse tangent 0.8. That can't be right. Oh, I didn't. Aha. So I got, here's something, and I'm going to show you. What I got was 0.67. Now, right away, I look at that and go, that can't be right. And part of the reason I say that is originally they said we tilt it to 20 degrees. So if this is sliding at an angle of 0.67, which is less than a degree, then that doesn't seem to make much sense. And sure enough, I look and my calculator is in radians. You will make this mistake at some point. I can almost guarantee you will have your calculator in radians, especially if you're going back and forth between this class and calculus. So we're going to switch it back. 2 degrees, and I'm going to try that again. Inverse tangent 0.8. That looks a lot better. Okay. So now you've seen me make a very important mistake and fix it. 38.6, I'll round that to 39 degrees. So 39 degrees is how far I'm going to have to tilt my dump truck to dump this out. Now the reason I did that first and not the other way around, let's go back up to the problem. It says, at what angle will the cabinet begin to slide? I did that first. It says, what is the magnitude of the static friction force when the bed is tilted at 20 degrees? Suppose I had done this one, the what angle, and I came out with something less than 20, like a 16-degree angle. Well, if the object starts sliding at 16 degrees, it will never make it to 20. In other words, there will not be a static friction force at 20, and the answer is just 0. So I'm kind of just testing it to see if that's true. As long as I get something larger than 20, I'm okay. If I get something less than 20, I don't even have to solve the first one. But I do. So if this, that's not true. So if we go to 20 degrees now, that's less than 39. I can be sure that the object will still be stationary at that point. So let's do that. What happens when it's at 20 degrees? Nope. There we go. All right. So I'm at an angle now of 20 degrees. This doesn't affect really my free body diagram that much. I just have to change the number to 20. So here I have the normal going off this way, the friction 90 degrees to the normal, and the gravity straight down. And we are assuming that the tilt is a 20-degree angle. So now what I have when I do my turn, right, if I go back to the normal up and the friction sideways and the mg sine theta forward and the mg cosine theta downward. So this still applies. That hasn't changed. What has changed is some of my numbers. And I'm looking for this. I want to know, what is the frictional force at that point? Well, the frictional force should be equal to the mg sine theta. And I believe they gave us the mass, I think it's a 50 kilogram filing cabinet. So I can just plug stuff in. The F is already solved for. I can plug in 50 kilograms here. I can plug in 9.8 meters per second squared here. And I know the angle. They told me that it's sine of 20. So I don't need to go bother with the normal force or the mu or anything like that. I can just do the frictional force based on the free body diagram. Okay. So let's just do that in our calculator here. 59.8 sine 20. And I get 167.5899 newtons. Where am I rounding to? It looks like this is a 2. No, I didn't. Bad me. This was a 50.0. I forgot my sig fig. So this is a 3 sig fig problem. So this would be 168? Yeah, 168 newtons. Cool. All right. A lot of being able to do free body diagrams there. The rotating tool, rotate your answer here like I did. That helps me. If it helps you, great. And let's go on to the next one. I think this is the last one here. Oh, how far? There we go. Whoops. Penguins, or penguins if you're Benedict Cumberbatch. So we've got penguins swimming, and anything that travels through, well, we've been talking about drag before, like through the air, but penguins have to deal with drag through the water. So let's look at the drag coefficient of a penguin in its swimming phase. And apparently somebody measured this, that when they had a 4.8 kilogram penguin, and this was how much it slowed down when it was gliding. So when it wasn't actively pushing itself forward, they were able to get its, well, I need this. They were able to get its acceleration. And they have it at what speed it had that acceleration. Now I'll modify this problem just a little bit because we're not going to be using the big drag coefficient equation. You will get questions like this on a test that will say, suppose the force varies with the velocity according to the following equation, F equals kv. That's what we mean when we say drag force varies linearly with the penguin's speed. In reality, I believe it's a quadratic. I believe it's kv squared, which we could do here. It's not be that bad. But I'm going to go ahead and say let's pretend it's linear because I think, especially if you're taking AP on the AP test, they like to use this format here, F equal kv. Anyhow, this is how drag works. The bigger your velocity, the bigger the drag force. So let's put a little d there to say that's the drag force. And let's draw our penguin, our penguin traveling through the water. He's gliding. And he's gliding not without pushing himself forward, so there's only, let's say his velocity is in this direction, then he only has one force on him, and that's backward. Technically, he has a buoyant force up and a gravity down, but those will cancel out and are not relevant to this problem. So here's the drag force. Very easy free body diagram. So with our penguin, let's do some givens. We have 4.8 kilograms is the mass. We have the acceleration is negative 0.52 meters per second squared. We have the velocity. The velocity is equal to 1.60, I ran out of room here, meters per second. And I think that's enough, yeah? Yeah. And we're looking for the drag coefficient, which for us will be k. K is going to be our constant that multiplies our velocity. Come on, there we go. So according to my free body diagram, sigma F equals ma, well, it's just this. F is the only force. equal to ma. But we also have that F equals kV. So I'm just going to set those two equal to each other because that's the same FD. So kV equals ma. And the final solve here is just going to be solving for k. So to get k by itself, I just divide by v. So k equals ma over v. And now I can plug in my givens. So the mass of this penguin is 4.8 kilograms. His acceleration is negative 0.52 meter per second squared. And we're dividing by a velocity of 1.60 meters per second. All right, let's plug all that in. 4.8 times negative 0.52 divided by 1.6. And I'm getting about 1.56. Negative 1.56, I suppose. I don't know that the negative is particularly meaningful in this problem. I guess all drag coefficients will probably be negative if we assume the motion is the forward direction. So I'm getting a k of 1.56, or negative 1.56. Meters and seconds cancel. I'm going to get kilogram per second as my unit, if that's useful. I guess if you kept everything in newtons, it would be newtons seconds per meter. But we could probably look this up on tables. I guess that would be the particular drag coefficient. I wouldn't worry too much about the unit here for a constant like this. So minus 1.56, which I believe is fairly small. I believe penguins are very streamlined. They don't have a lot of drag. If you were to compare it to something like a car has a lot more drag than a penguin. Because we build them, we don't evolve them. Okay, hopefully this was helpful in your problem-solving endeavors with force or drag force and friction force.